Hello everybody, welcome back to my channel, and in this video I will be showing you how to solve any type of quadratic equation. So if you're learning about solving quadratic equations, it's completely understandable if you feel overwhelmed. Sometimes the equation has two solutions, sometimes it has one solution, sometimes it has no solutions. Sometimes we can find the solutions by factoring, other times we can't factor the quadratic and we have to use either the quadratic formula or you may be asked to use the square root method. So trying to put all of that together and figuring out when you can do what and what to expect in solving these equations can definitely be overwhelming. But not to worry, I'm going to go through all of it. I'm going to show you exactly what to expect when solving a quadratic equation and how to find the solutions. In the video, I'm going to be using this note sheet that I have typed up with a bunch of examples and a bunch of information, and we're going to go through it and it's going to give us everything that we need. If you want to take notes with me along in the video, you can click the link in the description of this video and it'll take you to a page that looks like this, where you can print out the note sheet and follow along with me in the video. So let's get started. So just starting off, we want to talk about what is a quadratic. A quadratic is just a second degree polynomial. All that means is that the highest exponent that shows up is 2. And typically, we're very used to seeing quadratics in the form ax squared plus bx plus c. There's other forms that it can be written in, but for now we're just going to talk about that one form. So what are we looking for when we're solving a quadratic equation? When we're trying to solve this equation here, what we want to find are the values of x that when we plug them in to the left side of the equation, it comes out to give us 0. And later on in the video, I'll talk about why the 0 is so important and why we kind of want to, or in some cases, we want to stick with having 0 on one side of the equation. So here below this, I have a table with a bunch of different examples of quadratics and the graph, and I tell you what the solutions are. Later in the video, we'll look at all these different examples and how to solve them, but for now, let's just get an idea of what's going on. So in the first example, we have the equation x squared plus x minus 2 is equal to 0. This is what the graph of the quadratic looks like right here. On the graph, we can see that when x is negative 2, we get a y value of 0, and that when x is 1, we get a y value of 0. So the two solutions are negative 2 and 1. Remember, we're looking for the x values that would make y 0. Here's another example, example 2, that has the exact same solutions, but the graph looks different, and the equation looks a little different too. So it's possible to have more than one quadratic equation that has the same solutions. Here's another example, example 3, a quadratic equation, but the only place where that quadratic is equal to 0 is at negative 4/3. So this equation only had one solution. So sometimes we have two solutions, sometimes we only have one solution. Here's another example of a quadratic equation that has two solutions, negative 4 and 0.5. 0.5 is just a half, so I just wrote it as a fraction over there. So sometimes the solutions are integers, whole numbers, and sometimes the solutions are fractions. What's up with that? Here in example 5, we have another quadratic, two solutions of 0 and 2, looking for the two x values where that quadratic is hitting the x-axis, where it comes out being equal to 0. In example 6, here's another solution, or another quadratic equation, x squared minus 4, has two distinct solutions, two places where it's hitting the x-axis, negative 2, 0, and 2, 0. So I'm going to pause here at example 6. So far, all of the quadratic equations that we have looked at have had solutions, and the solutions have been rational numbers. All rational means is that you can write it as a fraction over another fraction. So for instance, negative 2 is negative 2 over 1. 1 is 1 over 1. So all of the solutions in examples 1 through 6 have been rational solutions. But here in example 7, quadratic equation, it has two solutions. But notice that when we look at the graph here, those solutions, those decimals there, those decimals, those are just approximations. So those are rounded answers. The exact answers, ignore that, are 3 minus root 2 and 3 plus root 2. So something's different between all of the previous equations and the equation that we have here in example 7, because the equation in example 7 has solutions that are irrational with those square roots showing up in the answer. We didn't have that before. And then examples 8 and 9, here are the graphs of those two. Notice that when you look at those graphs, neither one of those graphs ever touch the x-axis. In example 8, right there, this quadratic never touches the x-axis, that red line. In example 9, this quadratic never touches the x-axis, that red line. So equations 8 and 9 don't have any solutions. So again, I just show you all of that to say lots of different things can be happening in quadratic equations. So now let's take a closer look at what is happening when and why it's happening. So now that we've seen a lot of different scenarios and different things that can happen with quadratic equations, sometimes 2, 1, 0 solutions, sometimes rational, sometimes irrational, let's start looking at some details that's going to tell us what's happening when and how can we figure out what to expect. And once we know, what method could we possibly use to solve that quadratic equation? Now, I've organized this little flowchart tree diagram figure here that's in the note sheet if you print it out, that gives us all that information. And everything in this flowchart depends on the discriminant. What is the discriminant and how do I use it? So let's start talking about that. The discriminant of ax squared plus bx plus c is b squared minus 4ac. So you're going to find a, b, and c from the coefficients of the quadratic, and then you will plug them in and calculate that discriminant. Now both the value and the sign, and by sign I mean positive or negative, of the discriminant is going to give us information about how we can solve that quadratic equation and what kind of solutions we will find. So I'm going to break this up into 3 and then 4 cases. So the first case that we're going to look at is what happens when the discriminant is 0. So this first box here, we're going to talk about when the discriminant is 0. We're also going to talk about what happens when the discriminant is positive. If b squared minus 4ac gives us a positive number. And then the last scenario is what's going to happen when the discriminant is negative. So we're going to go in and analyze all 3 of those a little bit closer. So let's start with when the discriminant is 0. If b squared minus 4ac is equal to 0, that means that you can expect one real repeated solution. One real solution that is repeated. Just to remind you, that's what was happening up here in example 3. Up here in example 3, this quadratic only had one solution. There was only one place where that function was touching the x-axis. If your discriminant is 0, your options for solving the equation are factoring, quadratic formula, or the square root method. You can use any of those 3 methods. Now let's switch gears and talk about what happens if the discriminant is negative. So I'm going to skip over the positive part and let's talk about the negative. If the discriminant is negative, b squared minus 4ac less than 0. So I just wrote less than 0. All that means is negative. That means the equation has no real solutions. No real solutions. As a reminder, that's what was happening up here in examples 8 and 9. Examples 8 and 9 had no solutions. In example 8, that graph never touched the x-axis, and in example 9, that graph never touched the x-axis. So if we were to calculate the discriminant for 8 and 9, we would be getting negative numbers, which would tell us we're not going to have any solutions. At least not any real solutions. We would have imaginary solutions, 2 imaginary solutions. And to find those, you can either use the quadratic formula or the square root method. But regardless of which method you use, to write the imaginary solutions, you have to know that the square root of -1 is defined as the imaginary number I. We'll look at some examples where we get into that. Now let's talk about the 2 cases in the middle. Both of the cases in the middle deal with when the discriminant is positive, but I'm going to separate it down into the discriminant being a positive perfect square and the discriminant being a positive number, but not a perfect square. So if the discriminant is a positive perfect square, you can factor. You could use the quadratic formula, or you could use the square root method. But if the discriminant is just a positive number that's not a perfect square, you will not be able to factor. You will have to either use the quadratic formula or the square root method. So those three methods, factoring, quadratic formula, and the square root method, are the three methods that we'll talk about in this video as we go look at some examples. But there's a pretty big difference between the ones that we can solve by factoring and the ones that we cannot solve by factoring. And factoring is a pretty big deal. If your math teacher is particular, like I am when I have my students in class, if a quadratic equation can be solved by factoring, I always encourage my students to factor it. And I get it. Sometimes students are like, oh, but if I can solve it, why do I have to factor it? Why can't I just use the quadratic formula? Why can't I just use the square root method? Factoring is important, not just for solving equations, but for doing other things in math too. So I always encourage you, if you have the chance to factor, do factor. But then why is it so important to me? That brings us to our next section. Why is factoring so important? So here I'm just going to do a quick example. This part of the video is not really necessary in solving quadratic equations, but I'm a little extra and I like to give details. So I want to talk about why factoring is so important. Okay, so here is a quadratic equation that we would want to solve. So I'm going to draw three boxes here. I'm going to draw a box for the 2x squared, which we are adding to the 7x, which we are then subtracting 4. So this 4 box doesn't change, right? Because no matter what I plug in for x, when I start plugging in values for x, that box isn't going to change because there's no x in there. So what you're trying to do in this equation is you are trying to find values of x that when you plug them in, the whole thing, the blue box plus the purple box minus the green box, will come out to be 0. Note, that does not just mean you pick random numbers to go in those boxes. So like for instance, if you picked 8 to go here and 4 to go here, no, that wouldn't work. If you picked 8 to go here and -4 to go here, okay, that would work. Wow, that was embarrassing. Then 8 minus 4 minus 4 would give you 0. You can't just randomly pick numbers like that. You have to pick a value of x that when you plug it into the blue box and plug it into the purple box, you will get numbers that when you then subtract 4, it all equals 0. So for example, if I just randomly start guessing and I start off with picking x is 1, when x is 1 and I plug it into the blue box, I have 2 times 1 squared, which is 2. When x is 1 and I plug it into the purple box, I have 7 times 1, which is 7. And I would add those together and then I would subtract the green 4. All of this would give me 2 plus 7 minus 4, which is 9 minus 4, which is 5. But I want it to be 0. So 1 does not work. Then I could guess and pick 2. -1, -3, so on and so forth. If you keep playing this guessing game, you will very quickly realize that this is a boring game that is hard to win. It is very difficult to try to just look at that quadratic and find values of x that are going to work and make everything come out to be 0. But what if I change the game? What if I change the problem? What if I said, hey, look, you don't have to find values of x for the green box, the purple box, and the blue box? What if instead I rewrote this quadratic, instead of having it as like box plus box minus box, what if I was able to rewrite it where it was just one expression, one box, multiplied by another box equal to 0? And if I told you that what was in the first box was 2x minus 1, and what was in the second box was x plus 4. And then I wanted you to find values of x that made this equal 0. Now this is a lot easier, and this is why factoring is so important. Because if I want you to find values of x that make the product equal 0, all you have to do is get 0 in one of the boxes, and you're done. So for instance, if you're looking for values of x that are going to make either the red box or the orange box equal to 0, if x is -4, and I plug that into the red box, -4 plus 4 is 0. It doesn't really matter what's happening in the orange box. If x is -4, this is -8 minus 1, which is -9. But then when I multiply them, I get 0. So -4 is definitely a solution. Let's go see what would need to happen in the orange box. If I want the orange box to give me 0, what if I let x equal? Then you can look at that box and figure out what x needs to be. Or if you don't see it so easily, you can set that factor equal to 0, solve for x, and get x as a half. So if x is equal to a half, this is 2 times 1/2 minus 1. In the red box, we would have 1/2 plus 4. But going back to the orange box to simplify, these 2's cancel. And 1 minus 1 is 0, which would then be multiplied by 4 plus a half, which is 4.5. And that gives you 0. So that works. You're getting the 0 that you want. So it's a lot more straightforward to figure out what x needs to be if the quadratic is factored. That's the difference between the first game and the second game. Once you have it factored, so once you know the 2x minus 1 and the x plus 4, I'm going to erase the boxes just so it can look more like what it looks like when something is factored. Once you have it factored, it's a lot easier to solve the equation because all you have to do is set your factors equal to 0 and boom, you're done. So that is why factoring is so important. It's also why we have to do a little bit more work to solve a quadratic equation when it cannot be factored. So now that we have seen all this information about the discriminant, what it tells us, what kind of solutions we can expect, and what methods we can use, now we're ready to start looking at some examples. In our first example, we have x squared plus x minus 2 equals 0. Before we even get started with this example, I want to point out that all the examples in my video, I'm going to go ahead and have 0 on one side of the equation. If you're not given the equation in that form, so for example, if you're given x squared plus x equals 2, you would need to solve or get 0 on one side, not solve, but get 0 on one side of the equation. So you would subtract 2 like that, so your equation would look like this, okay? So the 0 on one side is important. We've already seen that factoring game with filling in the orange and the red box, that game only works if you have 0 on the other side. Doesn't work with any other number. Okay, so I'm going to get started and calculate the discriminant because the discriminant is going to give us a bunch of information. It's going to tell us if we can factor, what kind of solutions to expect, stuff like that. So the discriminant is b squared minus 4ac. I'm going to go and find a, b, and c, looking at the coefficients of the quadratic. The number in front of x squared, we don't see it, but it's a 1. The number in front of x, we don't see it, it's a 1, that's b. And the constant term with no variable, that's our c value. So c is -2. So now that I know all those values, let's calculate b squared minus 4ac. b squared is 1 squared, minus 4 times a is 1, times c is -2. 1 squared is 1, and be careful with your signs here. I see this, a lot of students mess up on this. You have a negative there and a negative there. Two negatives come together to make a positive. Then you can multiply the 4, 1, and 2 to get 8. And 1 plus 8 is 9, which is a positive perfect square. So that means that we can factor. So I'm going to solve this equation by factoring. So I'm starting with x squared plus x minus 2 equals 0. I want to factor this equation. A is 1. A is 1 here. And when A is 1, you can start the problem off, put an X in both of your factors, and then to fill in what goes here, we need two numbers that multiply to -2 and add to 1. Multiply to C, add up to B. It's kind of corny, but sometimes I tell my students multiply to see new things and add up to be great. I don't know, it helps them remember it, so maybe it'll help you. Okay, so two numbers that multiply to -2 and add up to +1 are +2 and -1. They multiply to -2 and they add up to 1. So I have my two factors. I have my red and my orange box that I want to multiply to be equal to 0. So what we have seen is that we need to set the red box equal to 0 and the orange box equal to 0. Either one of those being 0 will give us solutions. Solving both of these equations, I'll subtract 2 from both sides to get that x is equal to -2. Over here, I'll add 1 to both sides to get that x is equal to 1. So we have found the two solutions of that quadratic equation. They're two real solutions. All I mean by real is that there's no imaginary numbers, there's no I showing up. And that's what exactly we expected, because the discriminant was not just positive, but it was a perfect square, and so we were able to find those solutions by factoring. And they're two different solutions. And that concludes example 1. Now let's look at example 2. In example 2, and if you remember the table from earlier, this table up here, these examples are the same examples we're doing down below, okay? Examples 1 and 2 had the exact same solution. So let's take a look at that and see how that's happening. So in example 2, we have -3x squared minus 3x plus 6. I'm going to get started by finding a, b, and c, and then calculating the discriminant. A is the number in front of x squared, so a is -3 here. B is the number in front of x, which is also a -3, and c is the number that has no x with it, which is 6 in this example. Okay? Always make sure to take the signs with the coefficients, so take the negative with it. So I'm going to calculate b squared minus 4ac. That's our discriminant. B is -3, so we have -3 squared minus 4 times a, which is -3, times c, which is 6. So this is 9, just from -3 squared. Be very careful squaring negative numbers. As a teacher, side note, it is a pet peeve when you write this, but you mean this, okay? Because those are not the same thing. The second one means take -3 and multiply it by -3. Square -3. To get a +9. The first one just has a negative sign out in the front, no parenthesis. So again, I'm just going to stick a negative sign out in the front, but the squared is on the 3. So that would be 3 times 3. Well, -3 times 3 is a -9. So one's coming out negative and one's coming out positive, and your calculator understands the difference between those two things. So if you want to square a negative number in your calculator, make sure you're putting parentheses around that negative number, okay? I'm very particular about the way you write things because these things have a meaning. Okay, so again, careful with your signs here. Negative and a negative multiplied together is going to give us a positive, and then we'll multiply the 4 times the 3 times the 6. To give us a 72, and 9 plus 72 is equal to 81, which is again a positive perfect square. So that tells us that we can factor this quadratic. And I'm going to solve this equation by factoring. Now, if you know anything about factoring, you know that it's a little bit trickier when a is not 1. A was 1 in example 1, which is why we were able to just find two numbers that multiplied to C and added up to B. A is not 1 in example 2, so it would not be sufficient for us to look for numbers that multiply to 6 and add up to -3. That would not work here. But instead, if you notice, all three of these numbers, all three of the coefficients have something in common. They all have a -3 in common. So I'm going to factor a -3 out from that quadratic. So when I pull a -3 out from the first term, the negative 3x squared, it leaves me with an x squared. When I pull a negative 3 out from negative 3x, it leaves me with a positive x. And when I pull a negative 3 out from positive 6, it leaves me with a negative 2. Just a couple of quick things. When you're pulling out a negative, all of your signs should change. So we went from negative, negative, positive to positive, positive, negative. All those signs changed. Okay, so now we have a quadratic on the inside where a is 1. The new coefficient, the new number in front of x squared really is 1. So that piece I can factor by, again, finding two numbers that multiply to negative 2, multiply to c, and add up to 1. I'm getting 1 from the number in front of x. That's how you factor when a is 1. And that's the same thing we did before, because this x squared plus 1x minus 2 is the same thing we had up here in example 1. And we factor that with the red and the orange box, x plus 2, x minus 1. So I'll go ahead and fill those in. It's the same problem. I just multiplied it by a negative 3, which made the problem look very different, but it didn't change the solutions, and it didn't change the way we solved it. Now, I want to talk about this part because what I see a lot of people do, I'll get my boxes set up. What we've seen in the first example is we set the red box equal to 0. That's what gave us negative 2 as a solution. We set the orange box equal to 0. That's what gave us 1 as a solution. Now, what I'll see a lot of students do is they'll take this negative 3 out in the front and set it equal to 0 and tell me that negative 3 is a solution, which it is not. First of all, it's not possible for a quadratic to have 3 solutions. It's either 0, 1, or 2. Can't happen. Second of all, negative 3 is not a solution. If I plug negative 3 into this quadratic, we will not get 0 out. Negative 3 is just a number sitting out in the front. And if it bothers you seeing that negative 3 out in the front, what you could do from this point is you could go through this equation and divide both sides by negative 3 so that that will cancel out. And it will leave you x plus 2, x minus 1 equals 0 over negative 3 is still 0. And you're still going to get the exact same 2 solutions that we had before. So that wraps up example 2. That was for 2. Okay, so now let's look at example 3. And I'm going to get my calculator handy. I have a calculator here because it's just some pretty big numbers relative to what we're going to do. We're going to start off the same way we have been starting off, and we're going to find the discriminant so we know what to expect and how we can go about finding it. So I'm going to identify a, b, and c. A is the number that's in front of x squared. That's 9. B is the number that's in front of x. That is 24. And c is the number that has no constant, no variable with it. C is the number with no variable. It's the constant term, which is 16 here. I want to calculate the discriminant. I want to know what b squared minus 4ac is equal to. So that means I need to take 24, which is b, and square it, and subtract 4 multiplied by a, which is 9, and then multiply that by c, which is 16. If I was better prepared, I would have calculated this before hitting record, but I did not. So I'm going to calculate it, and I typed it into my calculator wrong. So, okay, I typed it in wrong again. Minus 4 times 9 times 16. I'm getting 0. Finally got it. So when the discriminant is 0, that means that we have one real repeated solution. I erased it from up here, but you have this written down if you're taking notes with me. One real repeated solution, and we can factor, and so I'm going to show you how to factor it. More specifically, if the discriminant is 0, it doesn't just mean that you have a repeated solution. It also means that your quadratic is something called a perfect square trinomial. Perfect square trinomial, which is really just a fancy way of saying that all of this 9x squared plus 16 plus 24x plus 16 can be rewritten as something squared. And if we could get our hands on that something squared, then we'd be pretty much done. So let's figure out how to find it. Once you know that your discriminant is 0 and you have a perfect square trinomial, it basically means that your quadratic is factoring like that, and that these two things should be the same. So it's not necessarily a red box and an orange box. It's a red box and a red box, because they will be the exact same thing that goes in those boxes. And I'm going to show you how to find that thing. Start with the first term, 9x squared. If your quadratic is a perfect square trinomial, then that first term is a perfect square, meaning that that first term is something squared. Obviously, it has to have an x in it because it has an x squared in it. And then how do I get 9? Well, I square 3. So it's 3x squared. 3x in parentheses, all squared. Whatever was in here, whatever you squared to get the first term, goes there and there. Now let's talk about what goes in the second blank, here and here. And it'll be the same thing. Look at your last term. Look at your last term. The last term is 16. If your discriminant was 0, if you have a perfect square trinomial, that constant term will be a perfect square. So it is something, I gave you the answer. It is something squared. It is 4 squared. A positive 4. Plus 4 plus 4. You may say, well, how do I know it's not a negative 4? Look at the sign here. If this is plus in front of B, this is plus. And this is plus. They're always the same thing in those two boxes if your discriminant was 0. So just to recap, we looked at our first term, 9x squared, and we figured out that we were squaring 3x. That's what gave us our first blank. We looked at our last term, 16. We figured out that we were squaring 4. That's what gave us the second blank. And it was because that 24x was positive that we know it would be plus signs. So now we have it factored, 3x plus 4, 3x plus 4. I'm going to erase this. I don't have to set 3x plus 4 equal to 0 twice. You can. It's not wrong to. And I know sometimes people can be very methodic when they're doing math and it just makes them feel more comfortable to do the same thing we've been doing and set both factors equal to 0. Perfectly fine to do that, but just know you're going to get the same solution. Subtract 4 from both sides of this equation to get that 3x is negative 4, and then I'll divide both sides by 3 to get that x is equal to negative 4/3, which is the same solution that we had up in the graph on the table for example 3. Okay, one repeated solution. That's what we're expecting when the discriminant comes out to be 0. One repeated solution. And if you were getting caught up on why is it repeated back earlier when we were talking about the discriminant, well, if you solve this equation too, you'd get the same thing. So that one solution shows up twice. And that is example 3. Another example where we could factor because the discriminant was 0. More specifically, we could factor it into a perfect square trinomial because the discriminant was 0. So now we're on to example 4. We have 2x squared plus 7x minus 4. This is the same example I used when I was explaining why factoring is so important. So yes, this quadratic can factor. I've already given you the factorization, but let's go through it again. To convince you that it can factor, I am going to calculate the discriminant. So I need a, b, and c. A is what's in front of x squared, which is 2. B is what's in front of x, which is 7. And c is the constant term with no variable, which is negative 4. So now that I know a, b, and c, I'm ready to calculate b squared minus 4ac, which is 7 squared minus 4 times 2 times negative 4. Be careful with your signs here. Again, I have a negative and a negative, so that will eventually come together to give me a positive. I like to go ahead and get that out the way because I don't want you to think that there's a minus sign there. That'll mess everything up. 7 squared is 49, and 4 times 2 is 32. And 49 plus 32 is 81, which is a positive perfect square. And I make a note of that because that tells me that we can factor. Now, remember earlier I said that factoring is not super straightforward when A is not 1. And our A is not 1, our A is 2. That's not 1. And we can't do the same thing we did in example 2 where we factored out that -3. Remember back in example 2? There's a lot of mumbo jumbo in here. But back in example 2, I was able to factor out this -3 because A, B, and C all had that common factor of -3 in them. That's not happening here in example 4. 2, 7, and -4, they don't have anything in common. So I'm going to show you how to factor a quadratic when you know that it can factor, but A is not 1. There's lots of different methods to do this. I'm going to show you my favorite method. So what I like to do is I like to take A and C and multiply them. So 2 times -4 gives me -8. Now I'm looking for two numbers that multiply to -8 but add up to +7. Two numbers that multiply to -8 but add up to +7. And two numbers that do that are +8 and -1. +8 and -1. They multiply to -8, they add up to +7. I'm going to rewrite the 7x term using those numbers. So I'm going to keep the 2x squared term in the front the same, but instead of writing plus 7x, I'm going to write plus 8x minus 1x. And then I'll keep the -4 the same at the end. So I haven't changed the problem because the 7x is the same as 8x minus 1. I've just made it more terms. And now I'm going to group. What I'm showing you is called factoring by grouping. I'm going to group the first two terms together, and I'm going to group the second two terms together, which ends after the -4. So looking at the first group, what I have underlined in blue, those two terms, in common, they have a 2x. I can pull a 2x out from those two terms and be left with an x plus 4 from factoring out that 2x. If I were to distribute this back in, I would get exactly what we have underlined in blue. Now looking at the second two terms, they have a -1 in common. I can pull a -1 out of both of those. And remember that factoring out negatives gives you sign changes. So you no longer have a -x, you have a +x. You no longer have a -4, you have a +4. Now this x plus 4 is showing up in both of them, in both the blue set and the green set. And if the quadratic can factor, it should always happen this way, where you have some common factor showing up between those two terms so that you can pull that common factor out. You can pull that x plus 4 out. The blue, when we pull out the x plus 4, just left us with a 2x, this 2x. The green, when we pull out the x plus 4, leaves us with a -1. That -1. So now I have the quadratic factored, and now I'm ready to go ahead and set both of my factors equal to 0 to, I'm just shrinking that down. I know it looks crazy, but I'm just shrinking it down to have some space to write. So I'm going to set the first factor of x plus 4 equal to 0, and I'll set the second factor of 2x minus 1 equal to 0. That factor and this factor. Subtract 4 from both sides to get the x is equal to -4. That's one of your solutions. Add 1 to both sides to get that 2x is 1, and then divide both sides by 2 to get that x is equal to 1/2. So there is an example of a quadratic equation that we solved by factoring, and more specifically, a was not 1. So the whole method that I used with the grouping and the breaking things down, that is called factoring by grouping, and it's one way that you can solve a quadratic equation that can factor when the leading coefficient, a, is not 1. We're going to start example 5, same way. We're going to find the discriminant. A is the number in front of x squared, a is 4. B is the number in front of x, b is -8. C is the constant term. Huh? There's no constant term. It's 0. I thought that was funny. If I could put a +0 right there. So basically what I'm saying is I could write this equation as 4x squared minus 8x plus 0 for you to see that C is 0. I know, I'm corny. Okay, so now that I have A, B, and C, let us calculate B squared minus 4AC. I'm going to plug in B, which is negative 8, square it. Remember my thing about parentheses, especially with negative numbers. 4 times C, which is 0. All that part just goes away because it's being multiplied by 0, and negative 8 squared is 64. That is positive, and that is a perfect square. So that means that we can factor. So let us factor this. Now in example 5, because there is no C term, it is very, very simple to factor this. There's no constant term to worry about, so if nothing else, we can definitely pull out an x because both of these terms have an x in them. So I know I can pull an x out. Even more so, between the 4 and the negative 8, they have a 4 in common. So I can pull out a 4x. So I have that factored out. On the inside of the parentheses, factoring out a 4x is going to leave us with x minus 2. And then we'll set both of those factors equal to 0. It's the same idea. Sometimes people think that like when the problem looks like this, it's not the same as the red box and the orange box that I've been drawing, but it is. It's just that the red box only has one term, and that's okay. You still set that first factor equal to 0, and you set your second factor equal to 0. I'm going to solve the red equation by dividing both sides by 4 to get that x is 0, and I'll solve the orange equation by adding 2 to both sides to get that x is 2. And we have our solutions, x equals 0 and x equal 2. Now let's look at example 6. In example 6, we have x squared minus 4 is equal to 0. Just starting off, finding the a, b, and c might be easier if you rewrite the equation as x squared plus 0x minus 4 is equal to 0. So I introduced this 0 here because there is no x term. So the number in front of x is 0. So we can see that b is 0, number in front of x squared is 1, a is 1, and the constant term with no x value, c, is negative 4. So now that I know a, b, and c, I'll go off to the side and calculate my discriminant of b squared minus 4ac, which is 0 squared minus 4 times 1 times negative 4. That's just plugging in a, b, and c. Very careful with your signs here. 2 negatives make a positive. 4 times 1 times 4 is 16. Positive 16, positive perfect square. And by the way, if you're ever going through these problems and you're not sure whether or not your number is a positive perfect square, just put it in your calculator if you can. So for example, when I put the square root of 16 in my calculator, I don't know if you can see that, you get 4. I'm sure people know that. But let's say you get some kind of big number like 179, and you want to know if that's a perfect square. Well, just type the square root of 179 in your calculator, like that. Focus. And if you start getting decimals, it's not a perfect square. If it was a perfect square, you wouldn't get decimals. Like another quick example, I know that 169 is a perfect square. So when I type the square root of 169 in my calculator, I'm getting just 13. So that lets me know that it's a perfect square. So that's just a quick way that you could check. Okay. So now that I know that it was a positive perfect square, let's factor it. So notice here that b is 0. If b is 0 and your quadratic can factor, so I'll make a note here, it was a positive perfect square and b is equal to 0. If b is 0 and your quadratic can factor, and we know that it can, since we got that positive perfect square, that means that you are working with something called a difference of squares. A difference of squares. So this is the second special type of quadratic equation that we have seen, because earlier we saw an example of a perfect square trinomial when the discriminant came out to be 0. I won't scroll to it, but we saw that example earlier when the discriminant was 0. But if the quadratic can factor and the b value is 0, you have a difference of squares, which means that your quadratic looks like a squared minus b squared. Don't confuse these a's and b's with these a's and b's. Okay, that's one downfall of math. The same letters get used over and over. And this always factors into a plus b, a minus b. So let's spend some time to figure out what these a and b are, what these a's and b's are, so that we can have the quadratic factored. So we have x squared minus 4 is equal to 0. Well, that's the same thing as, obviously, I'm just going to write it a little bit differently, x squared minus 2 squared. And the only reason I wrote it like that was so that we could clearly see that this x is this a, which is that a, and that this 2 that's being squared is this b, which is this b. So now all I have to do is fill this out, and I'll have it factored. Well, a was x, so that is x. B was 2, so that is plus 2. And a was x and b was 2. And so it's factored. If you didn't like my difference of squares demonstration, play the same game that we've been playing with factoring, right? You're looking for two numbers that multiply to -4 and add up to 0. That's -2 and +2. +2 and -2. Once you have your factors, set both your factors equal to 0. I'll solve both of these equations to get that x is equal to -2 and that x is equal to +2. And those are our two solutions there. Whoops, those are our two solutions there. And that concludes example 6. Okay, so now we're on to example 7, another quadratic equation. We'll get started the same way. Find a, b, and c. Find our discriminant. A, the number in front of x squared, is 1. You don't see a number in front. The number is 1. B, the number in front of x, is -6. C, the constant term with no x value, is 7. So we have a, b, and c. Let's calculate b squared minus 4ac, the discriminant. So we have -6 squared minus 4 times 1 times 7. -6 squared is a positive 36. And from that we are subtracting 4 times 1 times 7, which is 28. And 36 minus 28 is 6. No, it's not. It's 8. Okay, so yes, I'm a math teacher, and yes, I think I'm pretty good at math, but sometimes subtraction is just not my strong point. But I have other strong points. Anyway, we get 8, and that is not a positive perfect square. It is positive, but it is not a perfect square. So what that means is that we are in this case of our flowchart tree diagram thing. It was positive, but it was not a perfect square. So we cannot factor it. So if you are doing a problem and you do b squared minus 4ac and it's not a perfect square, don't even waste your time trying to factor that equation, because you will not be able to factor it. And if you can, please show me how. So we can either use the quadratic formula or the square root method. I'm going to go through this example showing you both methods, both ways to solve it, just so you can see. Sometimes teachers can be a little particular and say, solve using the quadratic formula or solve by the square root method. And if you don't use the method that you were told to use, you might not get any credit for that. So I want to show you both methods. And the first method I'm going to show you is the quadratic formula. The quadratic formula states, which if you're watching this video, maybe you're familiar with this. It's a lot of people's very favorite method to use to solve quadratic equations, because you just plug things in and you get your answers out. It says that the solution to this equation is negative b plus or minus the square root of b squared minus 4ac, that's our discriminant, all over 2a. Okay, so we're just going to be plugging things in here. X is equal to negative b. B is negative 6. Negative b. Be careful with your signs, okay? There was a negative sign from the formula, and then b was negative 6. Plus or minus the square root of b squared. So we are squaring that same negative 6 minus 4ac. A was 1, c was 7. And in reality, I didn't really need to write all that out under there because we already know that all of this under here is going to come out to be 8. Okay, but I'll simplify it in a bit. And this is all over 2 times a, and a is 1. So the signs are important because these two negatives right here will come together and make a positive. So this is just a positive 6 plus or minus the square root of 8 over 2. So I want to point out a couple of things. One, that really is 2 solutions. There's a solution with the plus, the 6 plus the square root of 8 over 2, and there's a solution with the minus, the 6 minus the square root of 8 over 2. Okay, so those are the 2 solutions. Some teachers may ask you to simplify that, and I'm going to show you how you can simplify it. So 6 plus root 8 and 6 minus root 8 all over 2. I'm going to erase this and just start with the solutions and show you how to simplify. And not all of these can be simplified, but this one can. So how you can know if it can be simplified is depends on what's under the square root. We have an 8 under the square root. Are there any perfect squares that go into 8? That's the question. Are there any perfect squares that divide evenly into 8? Sometimes the answer is no. If the answer is no, you couldn't simplify. But the answer is yes in this case. A perfect square that goes into 8 is 4. 8 is 4 times 2. So I'm just going to rewrite both of these as 4 times 2. And why I wanted a perfect square is because now I'm going to break this up. Instead of writing the 4 times 2 all under the square root, I'm going to write the square root of 4 and the square root of 2. The square root of 4 and the square root of 2, that's still all over 2. And again, I'm going to shrink this down just to give us a little bit more room. So now, because that 4 was a perfect square, remember we were intentionally looking for numbers that went into 8 that were perfect squares. The square root of 4 is 2. So this is 6 plus 2 root 2 over 2. And 6 minus 2 root 2 over 2. And then the last thing you can do to simplify is because all 3 of these numbers that are not under the square root, they all are divisible by 2. So I can divide all of them by 2 and be done. 6 divided, I'm going to rewrite them up here. 6 divided by 2 is 3. 2 divided by 2 is 1. The root 2 stays. In the bottom, 2 divided by 2 is 1. And I would get the same thing on the other side, but with the minus. It's supposed to be a 1 with the minus. And you don't have to write the 1 in the denominator, and you don't have to write the 1 that's in front of that square root. So this is 3 plus root 2 and 3 minus root 2, because things don't change when you divide them or multiply them by 1. So that's one way that you can find your solutions. Again, some teachers might just have you stop here. Depending on what level of math you're in or what grade you're in or what course you're taking, you might not have to simplify the square roots, but if you do have to, that's how you do it. Find perfect squares that go into that number and then simplify like that. And not every square root can be simplified. So we have gone through example 7 using the quadratic formula. And now I want to show you how to go through example 7 using the square root method, which is another method that you can use really to solve any quadratic equation, but specifically for the ones that can't factor. Because if you can't factor, again, I encourage you to factor. Okay, so solving using the square root method, we have to do something called completing the square. Eventually, I'll make a video on completing the square and upload it so you'll have that as a reference. But for now, I'm just going to show you how to do it. What we're going to do is we're going to move the 7 over to the other side of the equation. move the constant term to the other side of the equation. So we have x squared minus 6x is equal to negative 7. Then we want to add a number in right there on the left side, right after the negative 6x. But if I add a number in on that side, I also have to add a number in on the other side so that I'm keeping the equation balanced. And to find the number that you want to add in, you look at this negative 6. You look at b, the number in front of x, and you take it and you divide it by 2 and you square it. So we have negative 6 over 2 squared. So we have negative 3 squared. And so we have 9. So I'm going to add 9 on that side, and I'm going to add 9 on the other side as well. Now the purpose of adding that in is because if you do it correctly, this side of the equation will now factor into a perfect square. And it does. Two numbers that multiply to positive 9 and add up to negative 6 are negative 3 and negative 3. So that left side of the equation is just x minus 3 squared. And I'll combine the negative 7 and the 9 on the other side to get a positive 2. So we have that. Now remember, we're trying to solve for x. Shrink this down and give us a bit more room. We're trying to solve for x. So I need to get rid of that squared. So I'm going to square root both sides of this equation. I'm going to square root here and I'm going to square root here. But when you square root both sides of an equation, you have to put plus or minus in front of one side. You have to put plus or minus in front of one side. Square rooting gets rid of the squared on the x minus 3 and just leaves us with x minus 3 is equal to plus or minus root 2. There's the plus or minus that I needed. Remember, we're trying to solve for x. Let's get x by itself by adding 3 to both sides. To get that x is equal to 3 plus or minus root 2, which are the same solutions that we got before when we used the quadratic formula. Notice that here we didn't have to simplify that square root. It just came out already simplified. That doesn't mean every time you use the square root method that the square root will always be simplified. It was just a coincidence here. It's not always going to happen like that. But that's how you can solve example 7 by using either the quadratic formula or the square root method. So now we are down to our last two examples, examples 8 and 9. Round of applause for you if you have made it this far in the video. I'm proud of you. Keep it up. So if you remember from the table that we saw earlier, examples 8 and 9 were the two examples that had no solution. Meaning that if I look at their graph, the quadratics never equaled 0. They never touched the x-axis. It's better to say they have no real solutions because they do have imaginary solutions, which we saw on our little tree diagram flow chart, that when the discriminant was negative, no real solutions means we had two imaginary solutions, and we need to know that the square root of negative 1 is I in order to find those solutions. And the two different methods we could use are the quadratic formula or the square root method. So I'm going to use one method for one example and another method for another example just so you can see both of them. For example 8, I'm going to use the square root method because it's a little tricky. And I like to show tricky stuff. I feel like if you're here to get math help, I don't want to just show you the easy things. I also want to show you the hard things. It's easy to make videos about easy things. It's not so, you get what I'm saying. Okay, so example 8, we're going to use the square root method. I'm first going to calculate the discriminant just to convince you that the quadratic cannot be factored and that it does not have any real solutions. So I'm expecting to get a negative discriminant. A is 3, B is 6, and C is 4, picking off my coefficients. So I'm going to calculate B squared minus 4AC, which is 6 squared minus 4 times 3 times 4. 6 squared is 36, and 4 times 3 times 4 is 48. And I will not mess up on this subtraction. 36 minus 48 is negative 12. So I'm getting a negative answer. That's what's telling me that there are no real solutions. And this one I'm going to solve using the square root method. So the thing about the square root method is it starts off the same way, even when A is not 1, but then it gets a little bit different. That's why this one's a little trickier. So starting off the same way we did with the last square root method, we want to move the constant over to the other side. So I've subtracted 4 from both sides of this equation. And now, when you're doing the square root method, you need to make your leading coefficient 1. So I'm going to factor a 3 out from the left side of the equation because I want to have a 1 in front of the x squared. I'll leave this side alone right now. So when I pull the 3 out, I'm left with an x squared plus 2x. So I factor the 3 out. Now I can go and find the number that we add in after the x term. And whatever I add in after the x term, I'm going to have to put something on the other side of the equation to balance it out. The number that goes in here depends on b. Use the new b. If you had to factor that 3 out, do not go back and use 6 as your b. Use the new b, the 2. b over 2 squared, 2 over 2 squared, 1 squared is 1. So this is a plus 1 in there. This is where you have to pay attention. What a lot of people will do is say, oh, I added 1 on the left side of the equation. I'm going to stick a plus 1 right there. And that is wrong. That only works if your a was originally 1. But our a was not 1. Our a was 3. So when we put that plus 1 on the inside of the parentheses there, we have to remember we have it multiplied by a 3 in the front. So that's really 3 times 1, which is 3. So putting that 1 inside the parentheses really added 3 to the entire left side. So I need to add a 3 right there. Sometimes when I explain it like that, some of my students still don't get it. So what I tell them to do is start distributing this back out. 3x squared. Distribute that back out. 6x. Distribute that back out. 3. But all we started with was 3x squared plus 6x. We didn't have that 3. The 3 is what's new, so the 3 needs to also go on the other side. Okay, so that's why I wanted to do this one with the square root method, to show you what to do when that happens. So now we're back to a regular square root method. -1 and 3 give, -4 and 3 gives us -1. Sometimes I say the answers in my head. I say them out loud. I've thought of them already. Let's factor this x squared plus 2x plus 1. It is x plus 1 squared. Two numbers that multiply to 1 and add up to 2x. I'll just show you that real quick. I kind of skipped that step. But just factoring just that part underlined in red. Two numbers that multiply to 1 and add up to 2 are 1 and 1. So that's where I'm getting the x plus 1 squared. Another hint about the square root method, whatever this number is, the number that you squared to get that final answer, just the b over 2, that should always be this number. Okay, that should always be that number. So now let's solve for x. We need to isolate the squared. Isolate the squared. So let's get rid of the 3. I'm going to divide both sides by 3. So now I have x plus 1 squared is equal to -1/3. And then I'm going to square root both sides to get rid of the squared. And when you square root both sides, make sure you put that plus or minus. The square root and the square cancel out and just leave us with x plus 1 is equal to plus or minus the square root of -1/3. So now I'm going to shrink some of this down so we can have some more space, and I'll show you where the I comes from. So remember that the square root of -1 was I. The square root of -1 was I. So what I'm going to do is I'm going to rewrite that -1/3 that's under the square root as a -1 times 1/3. And then I'll break it up into the square root of -1 and the square root of 1/3. That's where my I comes from. Remember, the square root of -1 is I. So that gives me that I. The 1/3 stays under the square root and the plus or minus stays out in front. Okay, I'm just going to rewrite the equation up here so we can have some more space to finish solving it. I'm going to subtract 1 from both sides. minus 1, so that I can get rid of that plus 1 and solve for x. To get the x is equal to negative 1 plus or minus I multiplied by the square root of 1/3. There's again two solutions. There's a solution with the plus and there's a solution with the minus. You would get this same solution if you were solving this problem by doing the quadratic formula. And you could, and it would maybe be a little bit easier to use the quadratic formula because you wouldn't have to worry about all this 3 business and completing the square and all that nonsense. Well, it's not nonsense, but all that stuff. But just in case you had to use the square root method, that's how you would do it. In the last example, example 9, I'm going to show you how to do that one. We're just going to use the quadratic formula. First, let's go in and verify that we have no real solutions by calculating our discriminant. A is negative 5. B is the number in front of x. There is none. 0. C is negative 2. Let's calculate b squared minus 4ac. 0 squared minus 4 times negative 5 times negative 2. This is going to be negative. Go ahead and point that out. Negative, negative, negative. 3 negatives, an odd number of negatives, makes a negative. In fact, it makes a negative 40. Okay, so there we have the discriminant negative 40. Because it is negative, we know that we have no real solutions. Negative discriminant means no real solutions. I will remind us what the quadratic formula is here. And we'll just start plugging things in. So we have x is equal to negative b. B is 0, so you could not write it. Some people are very particular about following formulas. They put negative 0. That's fine. You can put the negative 0, or you can just not put anything. Or you can just put 0. Anyone, they're all the same. It's all okay. The nice thing about doing this off to the side here with the discriminant, if you're going to use the quadratic formula, you've already calculated that. We did it right there. And we got negative 40. And then in the denominator, we have 2a, which is 2 times negative 5. So we have plus or minus the square root of negative 40 over negative 10. The last thing we'll do is we'll simplify this down and we'll be done. So to simplify this, one, I'm going to go ahead and pull the I out. Okay. Remember that the square root of negative 1 is I. So you can take out the I and just leave a positive 40 under the square root because you took out the negative part. That's what gives you the I. Do not try to simplify things that are under square roots with things that are not under square roots. So do not look at that 40 over 10 and somehow say 40 divided by 10 is 4. You can't do that if the 40 is under the square root. So I'm going to simplify that square root. Same way we did last time. I'm looking for a perfect square that goes into 40. 4 does. I'm going to rewrite it as 4 times 10. Still over negative 10. Do not touch those 10s. Still, 1's under the square root. Separate. Leave the I. Break up the root 4 and the root 10. Keep it over negative 10. The whole reason you were looking for a perfect square is because the square root of 4 is 2. So now we have plus or minus 2 root 10 over negative 10. I. The I is still there, okay? 2i root 10 over negative 10, plus or minus. You can simplify things that are not under the square root together. So like the 2 and the 10 you can simplify. The 2 and the negative 10 in the bottom. 2 goes into both of those. 2 goes into 2 once. 2 goes into negative 10 5 times, negative 5 times, so that turns into a negative 5. Which leaves us with plus or minus. You don't have to write that 1. You do need the I. Root 10 over negative 5. And I'll mention that really you could drop the negative in the bottom. You don't need that negative 5 because the plus or minus is going to change the signs on it to give it either a positive or a negative. So it doesn't really matter if it was negative or not. But if that doesn't make sense, just ignore that last part and you have your solutions there. Okay, that is our last example. One, if you have watched this entire video, round of applause to you. This was a lot of information. I know it was a long video, but I wanted to give you a very thorough breakdown of how to solve quadratic equations, how to tell when you can factor, how to factor if you can factor, how to know when you can't factor, and how to solve when you can't factor and what different methods to use. If this video was helpful, please do like it and give it a thumbs up. And even if you did not like all the math in this video, you can still like my video. As Nancy Pye once said, you don't have to like math, but you can like my video. Thanks for watching. Subscribe, share, and I'll see you next time. Bye, everybody. Okay, that is our last example. 1, if you have watched this entire video, round of applause to you. This was a lot of information. I know it was a long video, but I wanted to give you a very thorough breakdown of how to solve quadratic equations, how to tell when you can factor, how to factor if you can factor, how to know when you can't factor, and how to solve when you can't factor and what different methods to use. If this video was helpful, please do like it and give it a thumbs up. And even if you did not like all the math in this video, you can still like my video. As Nancy Pye once said, you don't have to like math, but you can like my video. Thanks for watching. Subscribe, share, and I'll see you next time. Bye, everybody.